Hello, guys. This is 10.1. Starting a new chapter. We are going to look into the key component of Calc 2. So first, let's learn about sequences. So sequences is an ordered list of numbers. So let's say if I have a list of numbers, let's say 1, 2, 3, 4, 5, right? Like that, right? That can be called a sequence, or I can have something a little different, like 1, 1, 2, 3, 5, 8, and so on. And this is actually a really fun sequence, one of my favorite. It's called the Fibonacci sequence. Fibonacci, CCI sequence. Eh, Well, of course, we are not going to talk about the Fibonacci sequence now. I'll give you guys a little more details and how to find it later. So let's take a look at different types of sequences. So we can basically break it down into two types. One is a finite number of numbers in the list, or infinitely many numbers in the list. Right. So the finite number of lists would be like in the example what we have here: 1, 2, 3, 4, 5. Or it doesn't have to be different. You can have a list of numbers that's like 0, 0, 0, right? Like that. That's also a finite sequence. Infinite sequence would be like 1, 2, 3, 4, and so on, right? The all natural numbers. Right. Or the integers, right? Negative infinity, -3, -2, -1, 0, 1, 2, 3, and so on. Right? So those are the integers, right? Natural and integers. Okay. Now, notation-wise, for both finite or infinite, usually we use lowercase a to represent a number, an element in the sequence. So the first number in the sequence will be A1, A2, A3, and so on. And we have AN, AN plus 1, and so on. Right. So what these sub numbers mean, they basically tell you which term or which number you're looking at in the sequence. So for example, that will be the first term, second, third, and so on, right? And then a sub n, that will be the nth term. And an plus 1 will be the plus 1 term. Okay, so just some notation for representing either a finite sequence or infinite sequence. Now, another notation that we can use is by representing each term with a formula for the nth term, like that. Or if it's an infinite sequence, sometimes you will see that it goes from n equal to 1, right? The first term to infinite, right? If I wrote an and equals to 1 to 10, then this would mean that in this sequence we have 10 numbers from A1 up to A10, right? Um, and let's take a look at one quick example using formulas and different terms. All right, so let's say what we have here, the first term is 1/4, right? A1, A2, A3, A4, and A5. Okay, so in the first 5 terms, you can see down the bottom we have n equals to 1, 2, 3, 4, and 5. So all that means is that these 1/4 is the first number in the sequence, 2/9 is the second, and 3/16 is the third, and so on. Okay, so one interesting part with sequences is that how can you determine the nth term, right? So here we're actually given the formula for the nth term. So this would be our first type here, where it gives you the formula for the nth term, and then using this formula, you'll be able to find any term in the sequence. So for example, if I want to find the 10th term, all I need to do is plug in 10 as n, right? So plug in here. So we have 10 over 10 plus 1 square, which is 10 over 121. And that's how it's done. Okay. Now, of course, there are many different types of sequences, and this is going to be the fun part for this section. All right, now we can actually use the formula and understand it as a function, and then work out the order pairs, right? For example, we have here n is 1, and then 1, 4 will be a1, and so on, right? And we get many different order pairs, and we can actually use this the collection of order pairs to graph it, and it will look like this, right? So you can see that on the horizontal axis we have the value of n, right, up to 50 here, and you can see that it looks like a decaying exponential graph, and when you take the limit as n approaches infinity, we actually get 0. That means when we look at the sequence at the very end, towards the end, it will be some value very close to 0, right? We can actually give that a try. Let's say I want to do a sub 100, right? That will be 100 over 101 square, right? Which is a very small number. Let's see, around, so it's actually around 0.0098. Now, of course, you can pick a larger n value, and then the value in the sequence is going to be very small. Okay, so that's our first quick example. So in general, if the sequence are approaching some constant L as n approaches infinity, that being said, another way to say that is if we take the limit as n approaches infinity of an, right? So we're looking at large nth elements in the sequence. If it's equal to some constant L, then we say that the sequence is convergent, right? You can say that the sequence is convergent. Okay. Now, on the other hand, if the limit as n approaches infinity of an does not exist, or if it is infinite, we say that the system or the sequence is divergent. Okay, and let's look at some example here. Okay, so let's actually look at our last example here. As we can see that when we take n to infinity, right, the limit is actually 0. That means at the end, towards the end of this sequence right here, we are getting very small number that's approaching 0. So in this case, we will say that this sequence is actually convergent because it's approaching 0. It's approaching a constant. Now, let me show you some examples where they are divergent. Okay, so let's look at the first one. We have the sequence has the formula cosine of n pi over 2. Now, when you pick different n values, it just oscillates between 0, -1, 0, 1, 0, -1, 0, 1, because we know that sine and cosine graph, they just go up and down, up and down, up and down. And in this case, we say that the sequence is divergent because it's always oscillating. So oscillating means like switching or alternating. It's just numbers taking turns appearing. All right, always oscillating between -1, 0, and 1, right? So there's no exact constant where when we take infinity, we see the function approaching, right? It's either going to be -1, 0, or 1, depending on which value you end up stopping at, right? So in this case, it's divergent because the limit does not exist, right? There's no specific constant that we can take the limit to. Now, another one is when we get infinity, when we take the limit. So like in this case, n squared over 2. So the degree of the polynomial is greater than the degree of the degree of the numerator is greater than the degree of the denominator. So from Calc 1, we know that the limit is going to go to infinity, right? Therefore, we can conclude that the sequence is divergent, right? So again, we have collection of numbers, right? And depending on when we go to the very end, right, or take n to infinity, what behavior we get, we can decide whether it's a convergent series, a convergent sequence, or a divergent sequence. And that being said, the technique in order to take limit to infinity is also very important here. For example, earlier in the semester, we learned about L'Hopital's rule, and in Calc 1, we have learned different theorems, different tools, the limit laws, the limits at infinity. There are many techniques to help us find the limit at infinity. So here, I just want to share some review with you guys. All right, so of course, the tools that we have, right, are the limit laws, limits at infinity, and the L'Hopital's rule. And there are some theorems that can be useful as well. For example, the first one, the squeeze theorem, right? If you can show that the lower bound and the upper bound of the limit that you want converges to the same value, then we can say that the middle one also converges to that value. So squeeze theorem, sometimes is also called the sandwich theorem, right? Unfortunately, we cannot eat this, but it's a fun little theorem. And also, number 2, when we take the absolute value of the sequence, if it goes to 0, then that says the sequence is going to go to 0. So actually, let me give you a quick graph to represent the second point, right? So let's say you have a sequence, and when you plot all the elements, it looks like this, right? So that's oscillating between positive and negative, but as you can see that as n increases, the whole thing is approaching 0, right? So in cases like this, we can also say that it's convergent, it's converging to 0. It's not like this, where you just go up and down, up and down, up and down, and then there's no signs of diminishing because it's just oscillating between maybe -1 and 0, like the example that we are looking at earlier. Okay, and the third one, sequence Rn, r to the power of n. This is very useful. Okay, so keep this in mind. Is convergent to 0 if r is between -1 and 1, right? An example would be like 1/2 to the power of n, right? When you take infinite power of n, this whole thing is approaching 0, right? Because your base is between -1 and 1. When you take powers of something like that, it tends to decrease. If r is 1, then 1 to any power is 1, so it doesn't matter what power you take. You are always going to get a list of ones, like 1 1 1 1 1 and so on, right? So in that case, we can say that the sequence also converges, and to be exact, the sequence converges to 1. Now the last one is the divergent part, is when the value of r is greater than 1 or less than -1. So this is a very nice table that summarizes our third point right here. Okay. So this real line tells you your R value. If your R value is between 0 and 1, it converges to 0. At -1 and 1, it converges exactly to 1. Oh, sorry, not -1, right? Only +1. If it's 1, then it converges to 1. Right? Everything else is going to diverge, right? For example, -1, if you look at the sequence with -1 to the nth power, right? That's just going to oscillate between -1, 1, -1, 1, and so on, right? So in this case, this is actually divergent because when you take the limit to infinity, it's does not exist, right? It's either 1 or -1, but we cannot tell for sure which one we're going to get. And that's what makes the limit undefined. Okay. And the fourth one, we have if their limit approaches L and the function or the formula for the sequence is continuous at L, then we can say that when you take the limit of the function at an, which is the limit of an, which is equal to f of L. Now we'll actually look at this in details a little later. Fifth, every bounded and increasing sequence and every bounded and decreasing sequence is convergent. Okay, so this is very interesting, this point right here. So think about this. Bounded means there's ceiling or a floor that is stopping the function from going over or under, right? So let me draw a little picture to explain what this is doing. Okay, so 5 would say bounded and increasing. Right, so let's say this is my graph, and then we have a ceiling right here. Let's call that L. Right, then what this function is going to be doing, or the sequence is going to be doing, is it's going to be increasing, but when it gets very close to L, it's going to be very close to L, but never crossing it because L is your upper bound, right? So in this case, most of the time, the sequence is going to converge to L. Now, similar idea for bounded and decreasing, right? We have a floor instead of a ceiling, right? Like that. And then our function or our sequence is now decreasing, right? Something like this, right? Very close to L. Okay. So all these 5 points, they are very useful when determining whether a sequence is convergent or divergent. Now, of course, this is what we're going to be doing a lot in this section. All right, let's look at our first example. Determine whether the sequence converges or diverges. If it converges, find the limit. All right, so we have the formula for the sequence, right, an, and let's actually do a little practice. Let's find out the first 3 elements in the sequence, right? So a1, that will be 3 plus 5 over 1 plus 1, which is 4, right? And a2 is going to be 3 plus 20 over 2 plus 4. That's what, 23 over 6. And the third one is going to be 3 plus 45 over 3 plus 9, which is 48 over 12. That's a 4. Okay. So, of course, just by looking at the first 3 values in the sequence, it's very hard to tell if the sequence is going to converge or diverge, right? So the technique, just like what we were doing earlier, is by taking the limit of an as n approaches infinity, right? And let's evaluate this limit and see what we have. Okay, we have 3 plus 5n squared over n plus n squared. Now, one of the technique from Calc 1 is when you're taking the limit as n approaches infinity of polynomials having the same degree, then the limit is just the quotient of the leading coefficient. Right? So in this case, it's going to be 5 over 1. Right? But let's do a quick review on how to do that. Right? So the technique is you are going to multiply the numerator and denominator by the highest power of n that you see in this expression, right? So the highest power of n that you see is n squared. So we're going to multiply top and bottom by 1 over n squared. Okay. And by doing this, what you will have is after you distribute the 1 over n squared, you will have 3 over n plus 5 over 1 over n plus 1, right? And in this case, once you take the limit as n approaches infinity, the 3 over n term is going to go to 0, and the 1 over n term is going to go to 0, leaving you just 5 over 1. And that's how we can get the limit of 5. Right? Now, since when we take the limit as n approaches infinity and it approaches to a constant, then we can say that, yes, it's convergent, right? So to sum it up, we can say that the sequence an is convergent with limit of the sequence equal to 5. Okay. All right. Let's try another one. All right, next we have the sequence a sub n is equal to 1 over pi to the power of n. Now I want you guys to pause the video for now, take a few minutes and think about whether this is convergent or divergent, okay? All right, so the idea what we have here, 1 over pi, is your base, right? That's your base. And 1 over pi is approximately 1 over 3.14. And 1 over 3.14 is actually between 0 and 1. Right? So what we can do here is we can go back and use the technique right here, number 3. Right? The sequence r to the n, where you have a constant base to the power of n, and then we have 3 cases, convergent to 0, if that's the case, right? So we have our r is actually 1 over pi, which is between -1 and 1. So by this point, we can say that, yes, it's going to converge to 0. Okay. By number 3, an is convergent with limit as n approaches infinity of an equal to 0. Now, let's say you forgot, right? Let's say you forgot how point number 3, right? And you want to try to find out the limit, and it will still work, right? Let me show you. Okay, so I have 1 over pi to the nth power. Okay, so this is 0 point something, right? We don't care. Actually, I'm gonna type that into the calculator, and then we can use an approximation for 1 over pi. And that is about 0.32. Okay, and when you take a number like 0.32, any number between -1 and 1, and you take it to a very high power, it's always going to approach 0. Right? So it actually doesn't matter if you remember 0.3 or not. Of course, if you remember, then it can save you some time, but the actual taking the limit part is not going to be that crazy. Okay, all right, so let's move on to another one. All right, so next one we have -1 to the power of n minus 1 times n squared plus 1. And then here are our first few terms, right? So notice that if you look at the sequence, it's actually alternating in sign. So the first one is positive, the second one is negative, positive, negative, and positive. And the reason of this is because of this term right here, -1 to the power of n minus 1. What this term does is it's just alternate the sign, alternating sign, sign term. Okay. All right, so when n is 1, that's positive. When n is 2, that's negative. Right. So the -1 here is actually very subtle. It just makes the first term positive. Now, if you want the first term to be negative, then you can just have n, right? So if you just have -1 to the nth power, then it will look like -1, +1, -1, right? But if you want the first one to be first term to be positive, then you would just add a -1 here. Sometimes it can be a +1, but you know, it all depends on what you want to do. And in this case, it's not going to matter that much. All right, so let's see what happens for this sequence. Now, since it's alternating by point 2, by number 2, let me go back a little bit, right here. If we can show that the absolute value of the sequence converges to 0, then we can say that the sequence converges to 0. Now, notice that in this case, it has to be 0, right? It cannot be any other number because it's alternating, right? So it has to be 0, the only neutral number. All right, so let's take a look at this. By number 2, we can take the limit as n approaches infinity of the absolute value of this formula, meaning we can ignore the alternating factor, right? Just by doing n over n squared plus 1. Right now, in this case, the degree in the denominator is higher than the degree in the numerator, meaning it's going to go to 0, right? So we have shown that when we take the limit of the absolute value of the sequence and it goes to 0, then we can say that the limit of an, the sequence, is also 0, right? Therefore, it is convergent. Okay, so there are many techniques that we can use to show that the limit exists or it goes to 0. Now, it's gonna take a while for you to get used to this. So don't worry, we'll get a lot of practice with this. All right, this next example is I specifically picked this so I can show you the sandwich theorem, which is quite a little fun. All right. So first, let's consider the absolute value of the sequence, right? Notice that the sequence is again an alternating sequence, right? Oscillating between positive and negative, right? So let's consider the absolute value of it, which is just a sine of n squared over n. And that is much easier to work with. All right, so let's see. Our goal is to take the limit of this, right? But when you take the limit of this, it's actually very hard. So what we're going to do is we know that sine of n squared, right? Any sine function can only be between 0 and 1, right? Because the graph of sine oscillates between 0 and 1, -1 and 1. In this case, it's going to be 0 and 1 because we're looking at the absolute value of it. All right. Oh, I should include the absolute value here as well. Right. Okay. Right. And because of the absolute value, we don't have to worry about the alternating part, but we still could possibly get a negative sign from sine. So when we take the absolute value, we know that it has to be between 0 and 1, of course, including 0 and 1. And what I'm going to do now is I'm going to divide n to all of them. All right, give me 1 second. Let me just show you what I'm talking about. I'm going to take that inequality and divide everything by n. Okay, now we have a sandwich, right? The middle part is what we want, is the desired one, right? And then the outer part, they are very easy to work with, right? For example, we can show that this sequence converges to 0, right? Because, well, it's 0, right? 0 over n is 0. It all converges to 0. And 1 over n, when you take limit as n approaches infinity, 1 over infinity, that also converges to 0. Therefore, we can say that by squeeze theorem, or if you want, if you prefer, you can call that the sandwich theorem. By squeeze theorem, an converges to 0. Right? Oh, forgot the absolute value sign again in here. Okay. All right. So this is how you can use squeeze theorem. Most of the time, it can be used with sine or cosine because they just oscillate between -1 and 1. And when you add an absolute value, you can just say that it's between 0 and 1. Now, of course, we can also do this without the absolute value, making it a -1 instead of 0, right? And then -1 over, and that's still a convergent sequence that goes to 0. Okay. So again, there are many techniques that are being used in this section, and during our weekly meeting, we will take some time and work out a few more interesting examples. Okay, and that's it for 10.1. Thank you guys very much.